Let me introduce you to Paul Dirac. Paul Dirac wrote this book, Principles of Quantum Mechanics, in 1930. It still holds true today. He starts out by saying, why do we need quantum theory? And what I like to think of is the theory only comes into play when we start with macro objects that go along with macro physics, the physics that normally you start with in school. Uh, E equals 1/2 mv squared plus potential energy, things like that. Kinetic energy has a certain value, acceleration, velocity, so on, and even position. Dirac points out that when we get to the atomic scale, atomic physics, we have to create a new set of rules. But those rules have to also apply as we get to larger things so that it all becomes a continuous theory. You can't have one theory here and then another theory here that operates with the same kind of matter. So, where do we go? Where do we go? Where do we go? I've got some ideas that I pulled from the book as I slowly go through it, and Dirac says a lot in just a few words. One of the problems is the stability of the atom. Electron, proton, electrostatic force, the atom should just disappear real fast. You get a proton and electron, it should just disappear real fast. And I've got a little demonstration of that. And what else? What other things cause a problem when we start talking about them? Well, one of them is that if you disturb the system, you disturb an atom, then it should go into oscillations that could be seen with a spectroscope. In other words, the electron emits electromagnetic fields. Electromagnetic fields are really light, or it's ultraviolet or infrared, but the stuff that we can see is visible light. And then what happens is that doesn't occur. It doesn't occur at all. So you can come up with some more macro versions of ways to look at it, but it just doesn't fall into place. You don't get the spectral lines that you get from hydrogen that we were talking about earlier. Now, let me go on to another one. Experimental evidence of atomic behavior does not agree with specific heat. Specific heat, what's that? Well, the motion of the atoms and so on, and coming up with temperature. That's the way we measure the activity in there and can come up with this ideas of specific heat. Anyway, I've got a strong statement about this because I'm not the strongest on this particular one. Now, is that it? Is there anything else? The behavior of light at the atomic level is also a big deal. And one way to look at it is you can say a fraction of a photon is never observed. It's either one photon or no photon. If you cause the energy of a electron to drop, you emit a photon, and that's it. It's just one photon. So that kind of destroys some of your thinking along those lines. Also, the photon operates like a wave, but it also operates like a particle. An electron, a particle that we always agree is a particle, it also has wave type properties, and as it goes through physical slits that are very, 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 very tiny, it creates diffraction and interference patterns, just as if it was light. So we have to have some theory that involves wave and particle properties at the same time. Is that it? Atomic events cannot be described with the physics, the macro physics. I'm going to quit using classical physics and just call it macro physics because that's really what it is. It applies perfectly good at the macro level. Science can only deal with observables. And when you observe something, In the atomic world, say it's a little tiny speck of dust and you want to look at it with light, so you bounce light off of it. Guess what? That speck of dust moves. So you've disturbed the system when you look at it. Now, because of this, the results of our calculations can only be probabilities. They can't be exact numbers. So, a lot of what we talked about, and in some of the earlier videos, we talked about probability distributions, then that is where we're going with that. I think that's everything that Mr. Paul Dirac brought up. Stability of the hydrogen atom. This picture shows you that an electron now is approaching a proton, and classically or macroly, the macro way of thinking about this is the electron would be pulled towards the center of the proton, but it would be pulled there in decreasing orbits, just like a planet that would be orbiting the sun. And as it goes down, it would start going into, and eventually it would crash into the proton. So let's do some calculations based on macro physics and see what we come up with. Physicists calculated that the electron should lose all of its energy and spiral down into the proton in only about 1 second. In other words, the atoms should not exist longer than 10 to the minus 12 seconds. If that was the case, we'd have no hydrogen. We'd have pretty much, I don't know, I can't really imagine what that would be like. Here's another statement. The third law of thermodynamics is based on the combination of two ideals that are not achievable in practice: absolute zero and a perfect single crystal. Well, so far, okay, so what? Classical physics includes thermodynamics, but it does not use quantum mechanics or the theory of relativity. Therefore, the third law of thermodynamics is not explained by classical physics. That was that reference to specific heat that I mentioned. So that's a biggie. At this point, I'd like to make 3 points from Dirac's book. One is, how do we draw a picture of an atomic system? How do we draw a picture? That's rough. Second, how do we describe the state of an atomic system? And then, leading from these two, the third point is, what is this principle of superposition of states? And the superposition of states is the one that's going to be probably most troublesome for you at this point. A picture is not going to be detailed like macro physics is, where we can actually draw a picture of the items, we can sketch it out on a pad. Instead, our picture is going to use math to describe the situation. And to describe a situation, we have what we call the state of a system. Now, macroeconomics, macrophysics has a very definite state, and all the velocities, accelerations, positions, energies, all of those things can be calculated exactly. An atomic system, that's not the way it's going to work. The state is going to be described by fewer items because there's less that we can put our handle on. And the best way I can think of to introduce this or to make sense of it is, remember, the spectra of light is broken into clumps or wave packets called photons. So you get to the very smallest dimensions of light, and you're actually talking about photons. So, how do we describe this state then? Let me talk about the final point, which is superposition of states. I'm going to draw a little diagram here to help along with this, but let's look at my fingers here and see that there are slits in my fingers. If I have a quantum particle coming towards those slits, then according to quantum mechanics, there is a definite probability that the particle will go through this slit, but there's also a non-zero probability that it'll go through this slit. And there's a non-probability that it'll go through this slit. And if there's all a bunch of other little openings there, there's non-zero probabilities. So the superposition of states says that a particle can be more than one place at any certain time. How can that be? Well, remember the particles are wave-like. Photons are wave packets, electrons are wave packets, protons are wave packets. All of these things are packets, or let me say they're probabilities of where they might be. So for position, we can only come up with probabilities of those things. And the probability functions will help us describe what the actual probability numbers are for those items. So that's where we're headed with this. All right, let's review things. Picture of atomic phenomena. Any way of looking at the fundamental laws which make their self consistency obvious. In other words, something in your mind says, oh, I see how that works. State of a general atomic system cannot have the detail of a macro classical system that specifies all aspects with discrete numbers. Instead, we find that it ends up being probabilities. Superposition of states, which was stated by Dirac very well. The position or any other physical quantity is made up of an infinite, listen to that, infinite number of possible states, each with its own probability. Now, let's go down to this double slit experiment that I promised you we'd look at in a little more detail. See if I can find. Okay, this is interesting. This is Young, who did the original double slit experiment back in 1804. 1804, he passed light through double slits and it didn't match what they expected to happen. Go down here a little bit more. Don't want to bore you to death. And let's see, the link between, let's see, where are the electrons here? Somewhere there's electrons that shows a nice picture of it. Let me go down here a little bit further. Okay, here's Young's double slit experiment with single electrons. Here's the good picture. Let's see if I can get it all up there so we can see what's going on. Let me scroll down here a little bit so we can see the single electron. Here's the photon or a single electron. Now, if they go straight, boing, hit that, and you won't see anything on the other side. The electron or photon will get absorbed by whatever this darn material is here in red. But if the photon or electron goes this way, or it goes this way, let's see what happens on the other side. Whoops, let me scroll up here. Okay, they get refracted, and this shows an interference fringe so that it appears over here. But from looking at this, we also have an interference fringe over here. So it seems like it could be over here. So that single electron can cause two different interference fringes. Now, how small do these slits have to be? They have to be small enough that, excuse me, that they're equal to about one wavelength of this photon or electron packet. Let's see if there's some more information here that'll make us wow at this. Okay, let's see. In these experiments, Bach's team reduced the intensity of the incident beam so that only one electron was detected each second. Now, that's not very fast, thereby guaranteeing to greater than 99.999% probability that only a single electron was present between the source and the detector at any time. The experiment ran continuously for 2 hours, and initially the individual electrons appeared to arrive at random points on the screen, but as more and more electrons were detected, an interference pattern with bright and dark regions gradually emerged. So, let's go look at something from the physical review letters. Here's the double slit experiment published February of 2019. That was very, very simple, very, very recent. And this is not with a photon, not with an electron, but a single atom. That means this proves that all atoms, I guess you could say all matter, exhibits this same probabilistic behavior. So if you went to this link, you could actually read this thing about what happened in 2019 about showing the properties or the probabilities of a single atom and a double slit, each slit being equal to the, now listen to this, it is the wavelength of a atom. So you are not exempt from this. You're made of atoms, so this is inherent in all of physics.